All right, welcome. Math 123, Thursday from noon to 1 Eastern Time. And again, welcome everybody to class. Hopefully you had a great week. And we're going to get started with this quick today. As we go through today's class session, we're going to have a time where we're going to work in groups. So we'll have some virtual classrooms. I'm going to separate you. And if you're on a phone only, you won't be able to participate. So if you're on phone only, try to make this the last time that you're phone only, because we want you to be able to participate fully in what's going on and get the benefit of these activities. Okay, so when the class session breaks into its groups, a few things might happen. One is your screen will automatically go to that tab. You might have a new tab open, so it might open automatically. It might not open automatically. You might have to click on the tab, and you might get a notification that you have pop-ups blocked, so you might have to resolve that. And then when we go into our groups, you're going to see that you have a chat box that's specific to the group. Your microphone will be available specifically to the group. The whole rest of the class won't be able to hear you. Only the people in that group will be able to hear you. Okay, so if I've muted you, that won't affect. Okay, I just got a question in the chat. So if I've muted you, that does not affect what you hear. It affects what we hear from you. So if you can't, let me make a note here. I'm going to put this in the chat. If you can't hear, then you should restart the session. Okay, so in the future, if any of you are hearing this and you cannot hear, then you should, the best thing to do is just close it out and restart. Okay, that usually works. Check your settings on your computer. That might be helpful too. Okay, all right. So we're looking at page 24. And I want to actually bring your attention to page 23. I don't have it up on the screen, but page 23 has a chart on it, and it has names of numbers, what the standard notation is, what the power of 10 is. So we're going to be looking at scientific notation and ratios today. And so the first one here on page 24, it says here, writing out large numbers is cumbersome. This is where scientific notation comes in handy. In the procedure for writing a number in scientific notation, it says here, move the decimal so that there is one non-zero number in front of the decimal point. That means to the left of the decimal point. Write this number times the corresponding power of 10. So it shows an example of 12,000. The decimal point needs to go between the 1 and the 2, so there's only one non-zero number to the left of the decimal. And then the number becomes 1.2. And then we have to look at this and say, okay, the decimal in the beginning is at the right end. So if a number does not have a decimal in it, the decimal is automatically at the right end. And we had to move that decimal 1, 2, 3, 4 places to the left. And that's what that 4 means up there. Okay, so every time you move the decimal to the left, you add 1 to that power. Every time you move the decimal to the right, you subtract 1 from that power. So we moved it 4 places to the left. So that's why it's positive 4. Let's look at these numbers in these 4 problems here. The first one says 325,700,000, the approximate population of the U.S. So we're going to write that number in scientific notation. And so the decimal has to go right after the 3. Now the decimal in that number is all the way at the end. So we're going to put 3.257 times 10 and we have to ask ourselves, how many places did we move that decimal to get it between the 3 and the 2? And it looks like 8. Yeah, thank you for putting that in the chat box. I see some of you got that in there. Brianna and Alyssa, thank you. And remember again that your participation is required, so either by voice or by chat box at least one time per half of class, okay? So the next one says 7.3 billion. And if you look back on page 23, 1 billion is 10 to the ninth power. So we can just write this as 7.3 times 10 to the ninth. All right, or you can actually write the number out. 7.3 billion is 7,300,000,000. So if you wrote all that out, then you could just move the decimal however many places you need to. But when you have the word given, sometimes it's easier. Now the next one, if we write the next one the same way I did number 2, 92.96, and million is times 10 to the sixth power, that's not actually in scientific notation. It looks like it is, but it's really not. There's a problem here. What is the problem? What is the problem? Now, we don't need to round necessarily. Yeah, we have to have only one non-zero number to the left of the decimal. So it needs to be 9.296. Now, since we moved the decimal one to the left, we have to add one to the exponent. And it becomes 10 to the seventh power. All right, so now it is in scientific notation correctly. And then same idea with the next one. So why don't you try number 4? Just do it on your paper there or wherever. Don't put the answer in the chat box yet. But try number 4. And I'll give you a minute to do that. And then we'll talk about it. All right, so as we look at this one, we have 0.86 million, so times 10 to the sixth. And then since this is not correctly in scientific notation, we have to move the decimal one to the right. So it becomes 8.6 times 10. And since we move the decimal to the right, we have to subtract 1 from the power. It becomes the fifth. Yep, I see that some of you have that in there. Perfect. So now it says use a scientific calculator to perform the following calculations. And we don't even really need a scientific calculator to do this. We just need a calculator. So this is taking, number 7 is taking two numbers in scientific notation and multiplying to get them together. Number 8 is taking two numbers in scientific notation and dividing them. So there's a couple of rules we have when we're doing operations with scientific notation. And for adding and subtracting, which isn't here, but I want you to know that adding and subtracting, what we do is we take the least precise number, and that's the precision of our answer. So if I was going to take 7.935 and subtract 2.1, we would get 5385. However, since 2.1 was the least precise number, it's only to the tenths place, our answer has to end in the tenths place, so our answer would be 5.8. Now, when we look at multiplying and dividing, it's not based on the place value, it's based on the number of significant figures. So in number 7, 5.92 has 3 significant figures, 6.3 has 2 significant figures, so we should only have 2 significant figures in our answer. Regardless of where the decimal is, it doesn't matter. It's just that there are 2 numbers there, so our answer is only going to have 2 significant numbers also. What we're going to do is we're going to take 5.2, let's try that again. We're going to take 5.92, and multiply it by 6.3. So I'm going to take 5.92 multiplied by 6.3, and I get I don't get 5 point anything. Looking at my calculator wrong. Okay, we get 37.296. Now remember that our answer only has to have 2 digits in it. So 2 digits. I'm going to look at the next one and decide if the 7 stays the same or goes up. And because 2 is less than 5, it stays the same. So what we have to do next is take this number and put it in scientific notation. So it's going to become 3.7. Now up here, I'm kind of doing two things at once. Up here, we're going to add the exponents. So when you multiply, you add the exponents. And so it looks like 9 plus 5 is 14. So I'm going to do times 10 to the 14. And then because I had to move the decimal one place to the left, I'm going to make it 10 to the 15. So it becomes 3.7 times 10 to the 15. Okay. So let me go through that one more time, just so you have it. All right, so when I multiply the numbers, I get 37.296. We're going to add the exponents, 10 to the 14th. I realize that I can only have 2 digits in my answer, so I've got to move the decimal 1 to the left, and it becomes 3.7. And since I moved 1 to the left, we have to add 1 to the power. It becomes 15. So let's look at this division one. Same idea. We're going to divide the numbers, and we're going to subtract the exponents this time. So we're going to divide them in the order that they're given. So 1.9 divided by 4.62. And my calculator gave me 4.411255 times 10. And we're going to subtract the exponents. It looks like 13 minus 4 is 9. And then this is not in scientific notation, and we have too many digits. So again, this number here has the fewest number of significant digits, 2, and this is not in scientific notation. So we need to move the decimal 1 to the right, 4.1. We're going to drop the rest, and because the 1 is not 5 or higher, we're going to keep the 1 at 1, times 10, and since we moved the decimal 1 to the right, we're going to subtract 1 from the power, and it becomes 4.1 times 10 to the 8th. Okay, so there's a lot going on there. What I want you to do is I want you to take that information and apply it to these 4 problems. Now, if you flip your book to page 233, I'm going to separate you into groups. And so group A is going to do number 10, group B is going to do number 11, group C is going to do number 12, and group D is going to do number 13. So these are on page 233. All right. Group A is number 10, Group B is 11, Group C is 12, and Group D is 13. All right, so I'm going to separate you into groups. And remember, as I do that, there'll be a new pops up or a new tab. Make sure that you get into it. All right. Okay, so let's see. Everybody looks like they're in except Anna. or Anna. So Anna, let's see how I can help you out here. So Anna, there should be a tab that opened up for you. All right, Group D, working on number 13 on page 233. Can you guys show me that you found the chat box and are able to communicate that way, or voice with your voice communicate? Thank you, Stephanie. Anybody else find the chat box? Okay, Hannah, no jokes here. You said I can't, but you typed in it. This chat box, yes, perfect. Okay, we found it. And let's see. So Hannah and Stephanie, anybody else here? Sunging or Bowie? Find the chat box in here for your group. Make sure you guys introduce yourselves to each other. Perfect. Thanks, Bowie. Make sure you introduce yourselves to each other, either through the chat or through voice, and work out number 13. And we'll bring y'all back in just a minute here. Okay, so I brought you all back, and I hope that you were able to. It looked like everybody was able to get into a breakout room, so that's awesome. And let's take a few minutes here and check these answers. I didn't check with you to see what you got, but let's go ahead and check these. Let me skip my page, my page here.
Did you do that or did he?
All right, so for number 10, what did Group A, what did you guys come up with, by the way? Let me just have you put it in the chat. Multiplying these, we should have only 2 digits in our answer, and you do. And then we want to check the power. So we're going to take 3.8 times 5.7. When we do that, we get 21.66. Notice we only need 2 digits, and this is times 10 to the, we're going to add the exponents, 13. We're going to move the decimal one place to the left, and because this 6 is 5 or higher, the 1 is going to become a 2, so it's 2.2, just like you all have, times 10 to the, and we moved 1 to the left, so we're going to add 1 to the power, and it becomes 14. All right, so just like Kaylee had there. And number 11, so Group B, number 11. And Megan, that looks great. So how we get that answer? We take 3.28 times 5.16, and when I did that, I got 16.9248 times 10 to the, and we're going to add the powers again. And it looks like 7 plus 3 is 10. And we have to look and say, okay, I need 3 digits in my answer. I have to move the decimal one place to the left, 1.69. So these all just drop off because the 2 is less than 5, so we don't change the 9. We're going to add 1 to the power. It becomes 11. All right, so good job in Group B. And Group C, we did a division problem. What did you come up with? 2.9 times 10 to the third. Okay, let's check and see. We're going to do 2.3 divided by 7.9, and when we do that, we get 0.2911 times 10. We're going to subtract the exponents, so 7 minus 3 is 4. We only need 2 digits in our answer, so the 2 and the 9, we're going to move the decimal 1 to the right, and it becomes 2.9 times 10. Since we moved it to the right one, we're going to subtract 1 from the power, and we get the third power. That means 2,900 is what that actual number would be. And Group D, number 13. And your answers look good. So how do we get there? We divide 4.31 by 6.21, and in doing so, we come up with 0.6940, and then some other numbers. So I'll just put 4 and 2 on there, times 10, and we're going to subtract the powers. 11 minus 4 is 7. We need 3 digits in our answer since they both have 3, so we need the 6, 9, and the 4. Since 0 is less than 5, we're going to drop all that off. And we need to move the decimal one place to the right, so 6.94. Since we move the decimal 1 to the right, we're going to subtract 1 from the power, and it does become a 6. All right, super job, everybody. So let's go back to page 26. So on page 26, it takes the scientific notation, and it looks like we're going to write some ratios with it. And one of our important keywords is per capita. Now, before we start that, I want to ask, are there any questions on the scientific notation that we did? All right, awesome. Yes, if you move left, you add. Correct. Yes, if you move left, you add for each space you move left. If you move right, you subtract. This is from the exponent for each place that you move right. Thanks for getting that clarified, Aaron. So per capita, it says here, consider the ratio of Skittles to the U.S. population. If 200 million Skittles are produced each day and the U.S. population is approximately 324 million, the ratio of Skittles to people, or Skittles per capita, would be calculated as shown below. So 200 million divided by 324 million, the millions actually cancel each other out. So 200 divided by 324 is approximately 0.62 Skittles per person. So per capita means per person. And then to write this in a meaningful sentence, we'd say that it means that if all the Skittles produced in a day were distributed equally among American citizens, then each person would get 0.62 of a Skittle candy. Remember that per means to divide, so we're dividing by the people. So number 1 here says if there are 400 million M&Ms produced each day, find the number of M&Ms produced daily per capita. So in this case, we would take 400 million divided by the people, 324 million. And since they're both millions, we can just cancel that part off. And in dividing those, I got 1.23, yep, M&Ms per person. And then again, if we were to write a meaningful sentence, we would say something like, if all of the M&Ms produced each day were evenly distributed among American citizens, each person would get 1.23 M&Ms. So you can use this part here as a model. So number 2 says calculating values per capita can help us make comparisons. So we're going to make some comparisons in these next 3 questions. Number 2 says the National Center for Education Statistics, NCES, says that the state of Indiana spent $9.97 billion on K-12 students in the 2014-15 school year. If there were 1.05 million K-12 students in Indiana that school year, find the amount spent per student. So let's see. We want dollars per student. So we're going to take the dollars. 9.97 billion is times 10 to the 9th divided by 1.05 million, which is times 10 to the 6th. So notice in the previous question, we didn't put the powers on for millions because they were both millions. Now, since they're different, one is billions and one is millions, we do need to put the powers on. So this is dollars on the top, students on the bottom. And when we're dealing with these dollars, we're actually going to put it in terms of dollars and cents. We're not going to keep the answer in scientific notation. And so if we take those and divide them and if we use the scientific notation, we would get something like 9.49524 times 10 to the 3rd. And so that's $9,495.24 per student. And we're going to do the same thing for the Illinois students. So 28.54 billion. Now I know this isn't in correct standard, or this is not in correct scientific notation, but I'm just going to write the number up there so we have it. 2.05 million, so times 10 to the 6th. And then we're just going to divide those. And so when we divide those, make sure you get this on your calculator. We get $13,921.95. Oh, excuse me, 95 cents, yes. So number 4 asks us to make a comparison now and write a few meaningful sentences. So one way we could compare these is we could just subtract them and find out, what the difference is. So we could say something like Indiana spent about, it looks like about $4,500, $4,000 or so less per student than Illinois did in the 2014-15 school year. And so we could also say that Illinois spent about $4,000 more per student than Indiana did. And then another sentence we could have would be taking that a little bit further and quantifying it. And we could say that Illinois, so 4,000 is about almost 25% of Illinois' budget there per student. We could say that Illinois spent about 25% more per student than Indiana in the 2014-15 school year. Okay, so if I'm comparing Illinois to Indiana, then I have to take 4,000 divided by 14,000. If I want to compare Indiana to Illinois, I would take 4,000 divided by, I would take 4,000 divided by the 9,500, and then we could say that Indiana spent that percent less. So whatever that is, looks like 32. Thank you, Anna. I'm not sure, I didn't check that one. So, but that's the idea with the meaningful sentences. So let's look at page 28 and do a little bit more work with per capita. I want you to notice that the last column here says Starbucks per 100,000. So sometimes when we do per capita, we end up with numbers that are small and we can't really put our head around them because, look at Canada. What does 0.0000415 Starbucks per person mean, really? And so what we do is we say, okay, we can look at this per 100,000 people, and that make more sense. So multiplying the answer by 100,000, or moving the decimal 5 to the right, we get 4.15, and that makes a little bit more sense. There are 4 Starbucks per 100,000 people in Canada. We can understand that. So I'm going to do the US, and then I'll do the US and China with you, and I'll fill in the other values so you can see them, and then we can answer some of the questions there down below. So, only because we're running really short on time. So notice that the population here is in millions. So really for the US, I'm doing 6530 divided by 325.7 times 10 to the 6th, because it's millions. When you divide those, we get 0.0000, and I'm going to put 200, which, writing that in scientific notation, it is 2.00. I'm just keeping the 3 decimal places again. times, or the three significant figures, times 10 to the -5. If we multiply that by 100,000, we're really subtracting 5 from the exponent, or excuse me, we're adding 5 to the exponent, and it becomes a 0. Or we can take this answer and multiply it by 100,000, and we get 2.00. When I do China, I'm going to do 2936 Starbucks divided by the number of people, 1409.5 million, so times 10 to the 6th again. And that's going to give us an even smaller decimal. So I have, this time I have 5 zeros, and then 208. So this is 2.08 times 10 to the, I had to move the decimal 6 places to get there, so -6th power. And when I take this number and multiply it by 100,000, I get 0.208. So the US has 2 Starbucks per 100,000. China has 0.2 per 100,000, or 2 for every million people. The UK, 1.44 times 10 to the -5. And South Korea, 6.12 times 10 to the -6. And then we can answer these questions. So it says, use the number of Starbucks per capita for the US in a meaningful sentence. So we could say something like, in the US, so we're using the per capita, so we're using this value. We could say in the US, there were 0.00002 Starbucks per person in 2017. And that doesn't make a whole lot of sense. So let's look at the next question. Instead of per capita, calculate the Starbucks per 100,000 people for each country listed. Okay, so we did that. Use the Starbucks per 100,000 in South Korea in a meaningful sentence. So we could say something like, for every 100,000 people in South Korea, I do see your question, Aaron, give me just a second. For every 100,000 people in South Korea, there were 0.6 Starbucks in 2017. So let's see, Aaron's asking where I got the 0.208 from. So when I divided right here, I got 0.0000208. Writing that in scientific notation, it becomes 2.08 times 10 to the 1, 2, 3, 4, 5, 6, -6. And to get the per 100,000, if we take this number times 100,000, it's 0.208. So that's where the 208 came from. Okay. All right. So we are so running short on time, and I got 2 more things to talk to you about. Proportions, I think, or maybe just proportions. Okay, good. So we have enough time to do this. So it says here, proportionality occurs when the ratio of 2 quantities is constant. Mathematically, the 2 fractions are equal. So I want you to see how these are set up. It says we expect maps to be in proportion to the actual places they represent. The distance between Lafayette and Vincennes is 160 miles. It is represented by 6 inches on your map. If the distance between Lafayette and Fort Wayne is represented by 4.5 inches on the same map, how far apart are they in real life? So there's a couple of ways we can set this up. Now, to solve a proportion, what you do is you multiply the 2 numbers that are diagonal from each other and divide by the extra number. So if we were going to solve this one, we would multiply these 2 and divide by the 6. But I want you to see how it's set up because that's the most important part. Notice how this is Lafayette to Vincennes going down both inches, miles. Inches are going across. Notice inches and inches. Miles are going across, miles and miles. And then this is Lafayette to Fort Wayne. So part of the information is going down and part is going across. Same units go across, same city goes down. The answer is 120 miles. So let me show you more specifically why. Because this is 6 inches, 160 miles, 4.5 inches, we don't know how many miles. So when we multiply these two diagonal ones, we're going to get, what is that, 7,200, 720. We get 720 inches, miles. Then we're going to divide by 6 inches. So notice how the inches are going to cancel each other out, and we have 120 miles. And since we're trying to find miles, that answer makes sense. So you can always use the units to see if your answer makes sense. Now I want you to see how the next one is set up because it's the same question, it's just set up different. So here we have Lafayette to Fort Wayne across the top, Lafayette to Vincennes across the bottom. Top to bottom, we have inches in one column, miles in the other column. The answer is the same. Notice how we're still multiplying the 4.5 times the 160 and dividing by the 6. So again, it's about lining up your information. Okay, so let's look at these two examples I have and wrap this up. On page 32, we have a house assessed at $73,000 has an annual property tax of $1,600. How much property tax would the owner of a house in the same neighborhood expect to pay if his house was assessed at $87,500? Round to the nearest dollar. So in setting this proportion up, I guess there's really two ways we could do this. We could do house 1 and house 2. Assessed value, let me put the smaller number on the top. Tax and value. So house 1, tax $1,600. Value $73,000. House 2, tax we don't know. Value $87,500. So that's one way we could set it up. Another way we could set it up is we could do house 1 this way, house 2, we could do tax, and we could do value. So house 1's tax is $1,600. House 2's tax we don't know. House 1's value is $73,000. House 2's value is $87,500. So either one, we're still multiplying the $1,600 and the $87,500 and dividing by the $73,000. And when we do this, we get $1,917.81. But we're asked to round to the nearest dollar. So that would be $1,918. When you round to the nearest dollar, that means look at the dimes that you have, 80 cents, and decide if this number goes up or stays the same. And since it's more than 50 cents, the number goes up. All right, last one. I want you to take 2 minutes and figure this one out. Don't put your answer in the chat box yet. We'll get there. So I'm going to time it 2 minutes, set up and take care of number 6. Okay, can you guys find the hand raise feature and give me a hand raise if you set it up in one of these two ways? Either the now credit over dollars, summer credit over dollars, or credits next to the dollars, credits next to the dollars. Can you give me a hand raise if you set your problem up in one of those two ways? So here's what the numbers would have looked like. So that would be one, and then the other one would be like this: 1511, 19, 97, 25, X. Credits over dollars. You could have the dollars in the top also. You could have everything flipped upside down if you wanted to. So let me just check your hand raises here. All right, looks pretty good. So we're going to multiply the 11 and the 1997.25 in both cases, and then divide by the 15. And we do get the tuition as $1,464.65. All right, so don't forget that the orientation web work, web work 1 and web work 2, and the discussion board are all due by tomorrow, and web work number 3 and quiz 1 are due a week from tomorrow.